and got it published. And so that was the first solution to Einstein's field equation, and it's called the Schwarzschild solution, or the Schwarzschild radius. The thing is that when the Schwarzschild radius was solved, when Einstein field equations were solved for the first time, the result of the solution was nothing else than a black hole. Okay? That is, when he tried to solve the solution to calculate how much gravity something produces, you had to have infinite potential in the middle to solve it, meaning it creates a nonlinear infinite potential at the center. His equation predicts black holes. And that's why right away there was talks about how this equation could predict something like a black hole. But, you know, at the time this was highly theoretical, and nobody had ever thought that they would actually come across a black hole in the universe. So everybody basically ignored that part of the equation and said, well, we can use the weak curvature to predict, you know, the curvature of light around the sun, or how something would land on, you know, how much planets or how much galaxies, you know, they rotate and how they're organized. Now, this was very interesting, that the high curvature of the equation was never truly fully acknowledged, because when you approach the center of the equation with the curvature of space-time, the equation of Einstein goes towards infinity. So remember, I was telling you everything is a black hole because it's divisible to infinity. Well, here you have Einstein field equation telling you that it is so. That in fact you need that singularity in the middle in order to even calculate the weak curvature. And basically what we did is we used the weak part and we just let go of the other part unless it was called a black hole. What I'm saying here is that that first approximation had no rotation and predicted black holes. Okay? So eventually, with Elizabeth Rauscher, we wrote a paper. This is the title of the paper, The Origin of Spin, a consideration of torque and Coriolis forces in Einstein field equations and grand unification theory. This is a paper that's in peer review right now. It's a result of what I'm talking to you about. This is a new solution to Einstein field equations. Okay? There was a solution that was given to Einstein field equation after Karl Schwarzschild. It took a very long time. It wasn't given until 1965. In 1965, the Kerr and Newman solution was rendered, in which you had a black hole, or the object was allowed to spin and have charge. So it had spin, angular momentum, and charge. And it took all the way from Einstein writing these equations to 1965 before that was able to be figured out. So you can imagine the complexity. And this is basically the solution that's mostly used to interpret what we see around stars, black holes, galaxies, and all this. There's a problem, though. When you take these solutions and you apply them, for instance, to a galaxy or to the universal size, the result of the equation does not match observation. Okay? The result of the equation only predicts 4% of what we see out there. All right? That is, in order for the universe to look the way it does, or for a galaxy to look the way it does, with the amount of mass that we are seeing in that galaxy or in the universe, And when we put it in the Einstein field equation, it doesn't match. What they have to do, and what they've done, which I believe is a complete cop-out, is that they've added the 98 or 96% of the mass that's missing and the energy that's missing. They called it dark matter and dark energy. It's very, very convenient. Instead of revising the equation, they assume that it's something out there that they cannot measure and that they cannot see. So that's very convenient, because who can tell them it's wrong? Right? They've been looking for dark matter and dark energy since then. I mean, it's been, almost, at least 10 years of, funding and detectors and all sorts of experiments to detect dark matter and dark energy. Now, I think they will detect something. However, I don't think it's going to be what they think it is. I think the error is in the equation. And the error in the equation is describing, if this error would be corrected, would describe something that's out there, but that's not dark matter or dark energy. It's only a force that allows these dynamics to happen. And that force, I realized, had been omitted. And I'm going to show you how I found that out. I studied the Kerr-Newman solution that had finally added rotation into the space-time so that if an object was rotating, they could calculate that as well. The thing is when they did so, they wanted to get rid of complexity as well. Because angular momentum and gyroscopic effects are so complex, they did something very strange. They decided to eliminate the gyroscopic effects of rotation, like eliminating Coriolis forces and torque and things like precession and all this. Well, how would you do that? Well, the way they did this is that they attached the frame of reference to the rotating metric so that there would be no force. Now, this is a little trick that's used in physics and that really tweaks the results. And because this is buried under enormous amount of complexity and very little people on this planet understand these complexities, it is not being noticed until now. Now, what they did is this. Imagine this. You've got a shaft that's turning, maybe on the lathe here, right? Or maybe there's a V8 motor spinning this shaft, right? And it's spinning at 5,000 RPM and you're in front of it. And in a moment of illumination or in a moment of extreme stupidity, you grab onto that shaft. All right? With all your might. Well, you're going to experience some effects. Okay? Those effects have to do with shearing, like your skin flying off, heating, like smoke coming off your fingers, all sorts of effects like this that are certainly uncomfortable and that have to do with the force of torque applied now to your hands, right? That's forcing that shaft to spin. All the 300 horsepower of that V8 motor spinning that shaft. Well, if I grabbed you at the exact moment that you went to grab that shaft, if I grabbed you on your center of gravity and spinned you at the exact same rate, you would feel no force. You would feel no effects in your hand. It would be stationary relative to you. You see? However, I could still say that I'm accounting for angular momentum because I could count the turns that you're going around.